Hello everyone, this is Shreya Cintury from Namchi Government College, bearing roll number 21NS0310, third SEM BSc. So today we are going to look on the topic radioactivity. So before we go into the topic, I would like to show the topics that we are going to look today. First we have introduction, then discovery of radioactivity. After that, radioactivity, alpha decay, beta decay, gamma decay, laws of radioactivity, unit of radioactivity, applications, advantages, disadvantages, and after that, reference. Introduction. A.H. Becquerel discovered radioactivity in 1896 purely by accident. In radioactive process, particles or electromagnetic radiations are emitted from the nucleus. Radioactivity is the phenomenon in which nuclei of a given species transform by giving out alpha or beta or gamma rays. Alpha rays are helium nuclei, beta rays are electrons, gamma rays are electromagnetic radiations of wavelength shorter than X-ray. The SI unit for activity is becquerel, named after the scientist Henry Becquerel. 1 becquerel is simply equal to 1 disintegrations or decay per second. There is also another unit named Curie that is widely used and is related to the SI unit, as 1 Curie equals to 3.7 into 10 to the power 10 decays per second equals to 3.7 into 10 to the power 10 BQ. Radioactivity. When atoms become very heavy, neutrons are unable to bind and some nucleons keep on leaving the nucleus. These atoms or elements are known as radioactive elements, and process of spontaneous ejections of nucleons or radiation is known as radioactivity. There are three types of radioactive decay in nature: alpha decay, beta decay, and gamma decay. To get a closer look up onto radioactivity, let's look upon discovery of radioactivity, like when it was born and how. In 1896, Henry Becquerel was using naturally fluorescent minerals to study the properties of X-rays, which had been discovered in 1895 by William Roentgen. He exposed potassium uranyl sulfate to sunlight and then placed it on photographic plates wrapped in black paper, believing that the uranium absorbed the sun energy and then emitted it as X-ray. This hypothesis was disproved on 26th to mist of 27th of February when his experiment failed because it was overcast in Paris. For some reason, Becquerel decided to develop his photographic plates anyway. To his surprise, the images were strong and clear, proving that the uranium emitted radiations without an external source of energy, such as the sun. Becquerel had discovered radioactivity. Becquerel used an apparatus similar to that displayed below to show that the radiations he discovered could not be X-ray. X-rays are neutrals and cannot be bent in a magnetic field. The new radiations was bent by the magnetic field, so that the radiation must be charged and different than X-ray. When different radioactivity substances were put in the magnetic field, they deflected in different directions or not at all, showing that there were three classes of radioactivity: negative, positive, and electrical neutral. The term radioactivity was actually coined by Marie Curie, who together with her husband Pierre began investigating the phenomenon recently discovered by Becquerel. The Curies extracted uranium from ore and, to their surprise, found that the leftover ore showed more activity than the pure uranium. They concluded that the ore contained other radioactive elements that led to the discoveries of the elements polonium and radium. It took 4 more years of processing tons of ore to isolate enough of each elements to determine their chemical properties. Ernest Rutherford, who did many experiments studying the properties of radioactive decay, named these alpha, beta, and gamma particles and classified them by their ability to penetrate matter. Rutherford used an apparatus similar to that depicted in figure. When the air from the chamber was removed, the alpha source made a spot on the photographic plate. When air was At it, the spot disappeared, thus only a few centimeters of air were enough to stop the alpha radiation. Because alpha particles carry more electric charge, are more massive, and move slowly compared to beta and gamma particles, they interact much more easily with matter. Beta particles are much less massive and move faster but are still electrical charged. A sheet of aluminum 1 millimeter thick or several meters of air will stop these electrons and positrons. Because gamma rays carry no electric charge, they can penetrate large distance through materials before interacting. Several centimeters of lead to a meters of concrete is needed to stop most gamma rays. Alpha decay at first. So, as shown in the figure, in alpha decay, helium nucleus emits a mass number 4 helium nucleus and alpha particle. Alpha decay occurs more often in massive nuclei that have too large a proton to neutron ratio. In alpha decay, the atomic number changes, so the original or parent atoms and the decay product or daughter atoms are different elements and therefore have different chemical properties. Beta decay. Beta particles are electrons or positrons, electrons with positive electric charge or anti-electrons. Beta decay occurs when in a nucleus with too many protons or too many neutrons, one of the protons or neutrons is transformed into the other. In beta minus decay, a neutron decay into a proton, an electron, and an anti-neutrino. In beta plus decay, a proton decay into a neutron, a positron, and a neutrino. Both reactions occur because in different regions of the chart of the nuclei, one or the other will move the product closer to the regions of stability. This particular reaction takes place because conservation's laws are obeyed. In beta decay, the change in binding energy appears as the mass energy and kinetic energy of the beta particles, the energy of the neutrino, and the kinetic energy of the recoiling daughter nucleus. The energy of an emitted beta particle from a particular decay can take on a range of values because the energy can be shared in many ways among the three particles while still obeying energy and momentum conservation. Properties of beta rays. These are negatively charged particles, each having a mass and a charge equal to that of an electron. These are deflected by electric and magnetic field. This affect photographic plates and cause fluorescence in various materials. This produce less ionizations than alpha particles. These have a large penetration power greater than that of alpha particles. An aluminum sheet 1 centimeter thick can stop beta rays. These move with greater velocity, sometimes up to 90% of the velocity of light. The mass of a beta particles increases with each velocity according to Einstein's relativistic mass relation. Gamma decay. In gamma decay depicted in a figure, a nucleus changes from a higher energy state to a lower energy state through the emissions of electromagnetic radiations, that is photons. The number of photons and neutrons in the nucleus does not change in this process, so the parent and daughter atoms are the same chemical element in the gamma decay of a nucleus. The emitted photons and recoiling nucleus each have a well-defined energy after the decay. The characteristic energy is divided between only two particles. Properties of gamma rays. These are electromagnetic waves like light or X-rays, only having much greater energy, HV, and much smaller wavelength, lambda, than X-ray. These are undeflected by electric or magnetic field. These produce little or no ionizations. These have the strongest penetrating power. This can pass through many centimeters of lead. This affect photographic plates and cause fluorescence similar to X-ray. This travel with the velocity of light. They produce photoelectric effect when these are made incident on solid surface. Laws of radioactive decay. According to the law of radioactive decay, the number of radioactive atoms disintegrating per second is directly proportional to the number of radioactive atoms present at the instant of time. Mathematically, we can write that rate of decay equals to number of nuclei decay divided by time. So I have put my notes on it, pasted on it, so you can see the calculation through it. So at last we get, after calculating, we get the value n equals to n naught e to the power minus lambda t. N naught is the initial number of nuclei and n is the number of nuclei left undecayed at time. Here you can see the graph of n versus t. Half-life of decay, that is t half, the time in which half of nuclei decay and half remains undecayed. T equals to t half and n equals to n naught by 2. So calculating it, as you can see, after calculating the whole thing, we get t half equals to 0.693 divided by lambda. Number of nuclei left after n half-life can be calculated like number of nuclei after one half-life n equals to n naught by 2. By following the formula, we get second half-life. After second half-life, we get n naught by 4, and after 3 half-life, we get n naught by 8. After 4 half-life, we get n naught by 16. After n half-life, we get n equals to n naught by 2 to the power n. That is how we calculate the nuclei left after n half-life. Half-life graph can be seen like this. Activity of radioactive substance. Activity rate of decay divided by disintegrations. You can see by using the law of radioactive decay that we have seen earlier, the whole thing can be calculated, and at last we get the equation R equals to R naught e to the power minus lambda t. R naught is the initial activity and R is activity at time t. And the graph also can be seen in this manner. Now we have units of radioactivity. Units of radioactivity is been divided into three units. The first unit is the Curie. That is 1 Curie equals to 3.7 into 10 to the power 10 disintegrations. And the other one is Rutherford. So 1 Rutherford equals to 10 to the power 6 disintegrations per second. And the last one is the becquerel. That is 1 becquerel equals to 1 disintegration per second. Relations between different unit. 1 Curie equals to 3.7 into 10 to the power 4 Rutherford equals to 3.7 into 10 to the power 10 becquerel. Now we can see the advantages of radioactivity. Gamma rays are used to kill cancerous cells and hence used in radiotherapy. Radioactivity can be used mostly in hospitals and in industries. So let's look upon these advantages of radioactivity. High doses of radioactive radiations on the body might lead to death. Radioactive isotopes are expensive. Uses of radioactivity. Some radioactivity uses are provided in the point below. So all these resources, like the things that I have written here, are been taken out from this website shown, and the other one is NCERT book of class 12 and comprehensive physics volume 2. Thank you.